A complex adaptive system is a complex macroscopic collection of relatively similar and partially connected microstructures formed in order to adapt to the changing environment and increase its survivability as a macrostructure. They are complex in that they are dynamic networks of interactions, and their relationships are not aggregations of the individual static entities. They are adaptive in that the individual and collective behavior mutate and self-organize corresponding to the change-initiating micro-event or collection of events. Overview. The term complex adaptive systems, or complexity science, is often used to describe the loosely organized academic field that has grown up around the study of such systems. Complexity science is not a single theory, it encompasses more than one theoretical framework and is highly interdisciplinary, seeking the answers to some fundamental questions about living, adaptable, changeable systems. Typical examples of complex adaptive systems include the global macroeconomic network within a country or group of countries, stock market and complex web of cross-border holding companies, social, insect colonies, the biosphere and the ecosystem, the brain and the immune system, the cell and the developing embryo, manufacturing businesses, and any human social group-based endeavor in a particular ideology and social system such as political parties, communities, geopolitical organizations, war, and terrorist networks of both hierarchical and leaderless nature. The Internet and cyberspace, composed, collaborated, and managed by a complex mix of human-computer interactions, is also regarded as a complex adaptive system. The fields of CAS and artificial life are closely related. In both areas, the principles of emergence and self-organization are very important. The ideas and models of CAS are essentially evolutionary, grounded in modern chemistry, biological views on adaptation, exaptation and evolution, and simulation models in economics and social systems. The study of CAS focuses on complex, emergent and macroscopic properties of the system. John H. Holland said that CAS are systems that have a large numbers of components, often called agents, that interact and adapt or learn. General properties. What distinguishes a CAS from a pure multi-agent system is the focus on top-level properties and features like self-similarity, complexity, emergence and self-organization. A mass is defined as a system composed of multiple interacting agents, whereas in CAS, the agents as well as the system are adaptive and the system is self-similar. A CAS is a complex, self-similar collectivity of interacting adaptive agents. Complex adaptive systems are characterized by a high degree of adaptive capacity, giving them resilience in the face of perturbation. Other important properties are adaptation, communication, cooperation, specialization, spatial and temporal organization, and reproduction. They can be found on all levels. Cells specialize, adapt and reproduce themselves just like larger organisms do. Communication and cooperation take place on all levels, from the agent to the system level. The forces driving cooperation between agents in such a system, in some cases, can be analyzed with game theory. Characteristics. Some of the most important characteristics of complex systems are: the number of elements is sufficiently large that conventional descriptions are not only impractical, but cease to assist in understanding the system. Moreover, the elements interact dynamically, and the interactions can be physical or involve the exchange of information. Such interactions are rich, i.e., any element or subsystem in the system is affected by and affects several other elements or subsystems. The interactions are nonlinear. Small changes in inputs, physical interactions or stimuli can cause large effects or very significant changes in outputs. Interactions are primarily but not exclusively with immediate neighbors, and the nature of the influence is modulated. Any interaction can feed back onto itself directly or after a number of intervening stages. Such feedback can vary in quality. This is known as recurrency. Such systems may be open and it may be difficult or impossible to define system boundaries. Complex systems operate under far from equilibrium conditions. There has to be a constant flow of energy to maintain the organization of the system. Complex systems have a history. They evolve, and the past is co-responsible for their present behavior. Elements in the system may be ignorant of the behavior of the system as a whole, responding only to the information or physical stimuli available to them locally. Robert Axelrod and Michael D. Cohen identify a series of key terms from a modeling perspective. Strategy, a conditional action pattern that indicates what to do in which circumstances. Artifact, a material resource that has definite location and can respond to the action of agents. Agent, a collection of properties, strategies and capabilities for interacting with artifacts and other agents. Population, a collection of agents, or, in some situations, collections of strategies. System, a larger collection, including one or more populations of agents and possibly also artifacts. Type, all the agents in a population that have some characteristic in common. Variety, the diversity of types within a population or system. Interaction pattern, the recurring regularities of contact among types within a system. Space, location in geographical space and time of agents and artifacts. Space, location, in a set of categories structured so that nearby agents will tend to interact. Selection, processes that lead to an increase or decrease in the frequency of various types of agent or strategies. Success criteria or performance measures. A score, used by an agent or designer in attributing credit in the selection of relatively successful strategies or agents. Modeling and simulation. CAS are occasionally modeled by means of agent-based models and complex network-based models. Another method of developing models for CAS involves developing complex network models by means of using interaction data of various CAS components. Recently, Springer Open Biomed Central has launched an online open-access journal on the topic of complex adaptive systems modeling. Evolution of complexity. Living organisms are complex adaptive systems. Although complexity is hard to quantify in biology, evolution has produced some remarkably complex organisms. This observation has led to the common misconception of evolution being progressive and leading towards what are viewed as higher organisms. If this were generally true, evolution would possess an active trend towards complexity. As shown below, in this type of process, the value of the most common amount of complexity would increase over time. Indeed, some artificial life simulations have suggested that the generation of CAS is an inescapable feature of evolution. However, the idea of a general trend towards complexity in evolution can also be explained through a passive process. This involves an increase in variance, but the most common value, the mode, does not change. Thus, the maximum level of complexity increases over time, but only as an indirect product of there being more organisms in total. This type of random process is also called a bounded random walk. In this hypothesis, the apparent trend towards more complex organisms is an illusion resulting from concentrating on the small number of large, very complex organisms that inhabit the right-hand tail of the complexity distribution and ignoring simpler and much more common organisms. This passive model emphasizes that the overwhelming majority of species are microscopic prokaryotes, which comprise about half the world's biomass and constitute the vast majority of Earth's biodiversity. Therefore, simple life remains dominant on Earth, and complex life appears more diverse only because of sampling bias. This lack of an overall trend towards complexity in biology does not preclude the existence of forces driving systems towards complexity in a subset of cases. These minor trends are balanced by other evolutionary pressures that drive systems towards less complex states. Literature. Ahmed E. El-Ghazarez, Hagazias. An overview of complex adaptive systems. Mansoura J. Math 32. 6059. Arxiv, NLIN 05060059. Bibcode 2005 NLIN 6059A. Arxiv, NLIN 05060059V1. NLIN AU. Bullock S. Cliff D. Complexity and Emergent Behavior in ICT Systems. Hewlett-Packard Labs. HP 2004-187. Commissioned as a report by the UK government's Foresight Programme. Dooley, K. Complexity in Social Science Glossary, a research training project of the European Commission. Edwin E. Olson and Glenda H. E. O. Yang. Facilitating Organization Change. San Francisco. Jossie Base. ISBN 0-7879-5330-X. Gelman, Murray. The Quark and the Jaguar. Adventures in the Simple and the Complex. San Francisco. W. H. Freeman. ISBN 0-7167-2581-9. Holland, John H. Adaptation in Natural and Artificial Systems. An Introductory Analysis with Applications to Biology, Control, and Artificial Intelligence. Cambridge, Mass. MIT Press. ISBN 0-262-58111-6. Holland, John H. Emergence. From Chaos to Order. Reading, Mass. Perseus Books. ISBN 0-7382-01421-1. Solvert, Samuel. Dimensions of War. Understanding War as a Complex Adaptive System. Paris, France. Harmattan. ISBN 9782296-99721-9. Kelly, Kevin. Out of Control. The New Biology of Machines, Social Systems and the Economic World. Boston. Addison Wesley. ISBN 0-201-48340-8. Farrow, M.C. Looking to Systems Theory for a Reductive Explanation of Phenomenal Experience and Evolutionary Foundations for Higher Order Thought, retrieved 15 January 2008. Hobbs, George and Scheepers, Renz, Agility and Information Systems, Enabling Capabilities for the IT Function, Pacific Asia Journal of the Association for Information Systems, Volume 2, ISs. 4, Article 2. Link